The components of a vector or a tensor depend on the basis that we use to describe it. In particular, as we have been considering coordinate bases, let us consider two different coordinate systems. Let's call them chi-a and chi', respectively. Then the primed tangent vector basis is going to be given by the partial derivative of the position vector with respect to the primed coordinates. Using the chain rule for partial derivatives, this can be rewritten as the partial derivative of the position vector with respect to the unprimed coordinates multiplied by the partial derivative of the unprimed coordinates with respect to the primed coordinates. But this is equal to the partial derivative of the unprimed coordinates with respect to the primed coordinates multiplied by the unprimed tangent vector basis. And this follows from the fact that the partial derivative of the position vector with respect to the unprimed coordinates is the definition of the unprimed basis. We can do the same thing for the dual basis, so let's take the primed dual basis vectors, which are defined as the gradients of the primed coordinate functions. Again, using the chain rule, we find that this is equal to the partial derivatives of the primed coordinates with respect to the unprimed ones multiplied by the gradients of the unprimed coordinate functions. So this is all equal to the partial derivative of the primed coordinate functions with respect to the unprimed coordinate functions multiplied by the unprimed dual basis. And this is because the gradient of the unprimed coordinate functions is equal to the unprimed dual basis. Given these relations between the primed and unprimed basis vectors, we are ready to find how the components of a general type NM tensor T depend on the coordinate system. In particular, looking at the components in the prime coordinate system, which we will write T A1 prime through AN prime, B1 prime through BM prime. This is by definition equal to T acting on the primed tensor basis E prime A1 prime through AN prime acting on the primed tangent basis vectors. Based on the transformation properties of the basis vectors, this is equal to the product from k equal to 1 through n of the partial derivatives d chi prime ak prime d chi ak multiplied by the product from L equal to 1 through m of d chi bl d chi prime bl prime times T acting on the unprimed tensor basis E a1 through an acting on the unprimed tangent vectors E b1 through E bm. Carrying over all of the partial derivatives here, we notice that what remains here is the tensor component of the tensor T in the unprimed coordinate system, T a1 through an, b1 through bm. And this therefore tells us how the tensor components in the unprimed coordinate system relate to the tensor components in the primed coordinate system. As an example, let's consider vectors, which we will here consider as type 10 tensors. That is, we will write them in terms of the tangent vector basis. A vector v can then be expressed as va multiplied by the tangent basis vector ea, or equivalently in the prime coordinate system as va prime e prime a prime. However, we know that the contravariant components in the primed coordinate system va prime should be inner product of the primed dual basis vector with the vector v itself. Expanding the vector v in terms of the unprimed basis, we therefore find ea prime inner product with va ea. By writing out the definition of the basis vectors here, this can be written as va times the gradient of chi prime a prime inner product with the derivative of the position vector with respect to chi a. Using the chain rule in reverse, we find that this is va times d chi prime a prime d chi a. And we note that this is precisely the transformation rule that we get with n equal to 1 and m equal to 0 in the above derivation. That is, we have n different from 0, which gives us the terms which have the derivatives of the prime coordinates with respect to the unprimed ones, but we do not have any terms where we have the derivative of the unprimed coordinates with respect to the primed ones.